Good morning, my name is Bobby Coffin and today I'll be presenting my second update for MANE 4240 Finite Element Analysis course. And my project is on temperature distribution and steady state heat conduction through zirconium dioxide on an Inconel. This project number 2 update is going to go through defining the variables that I've chosen to use, showing the tests that I have currently completed, going over the course tools that will be utilized and additional tests that I need to complete, and then ultimately the output status and additional steps in order to complete the project. The primary focus of this project will be to show the temperature distribution and the impacts of the thermal barrier coating the zirconium dioxide on an Inconel 100 plate. I've decided to set the thickness on the Inconel 100 plate as a constant and then currently vary the thickness for the zirconium dioxide to 4 different values and see the thermal effects of that. I have also set the temperatures of the hot side and the cold side to 20 degrees Celsius to 1037 degrees Celsius. These numbers were chosen based on 20 degrees Celsius equaling room temperature, about a 68 degrees Fahrenheit, and the 137 degrees Celsius equaling 1900 degrees Fahrenheit, which Inconel experiences rupture stresses at. In regards to the applicability of the project, I'm just going to talk about the differences since the last times I updated this. By changing the coating thickness, it'll demonstrate the best benefit to the metal, which at the applicability from manufacturing and assembly side of can you increase the coating thickness of the zirconium dioxide and ultimately create a better effect for the Inconel 100. So that's what my results I'm hoping to show. In the final project, you will see the following models being used: Maple for the 1D models and COMSOL for the 2 and 3D models. In this report out, you'll see Maple examples. In this Excel file, I have exported the data from Maple doing my 1D modeling to use the Inconel 100 plate as a constant thickness and then varying the zirconium dioxide by 3 different thicknesses and showing the impact to the 4 temperatures, the exact solutions that get calculated, and then ultimately also showing the amount of error difference between the Glerkin method and the global finite element method, and the fact that they're very, very accurate methods, but at 1 thickness, the error actually is 0. On this slide, you will see the graphs that I've created through Maple 1D modeling on the 4 different tests that I have generated. Test 1 is the thinnest coating of the zirconium dioxide, and test 4 is the thickest example that I used. So the top graphs of each of the 4 tests show the temperature as a function of the distance from the hot to the cold side of the plate. And on the bottom graphs, you'll see the conductivity between the 2 materials. You will see in all 4 scenarios a drastic difference between test 1 and test 4, which is the thinnest scenario to the thickest scenario of the coating. So it does show that that thermal barrier makes an impact on the results to the substrate material, that Inconel 100. These graphs shown on this slide were also created through Maple on the 1D modeling process. And the 4 tests are showing the global finite element with the 2 layers of the coating, the TBC coating, which is much tighter of an X as shown due to the thickness of the coating. You can see the difference as we move to the right. Test 4, the spacing obviously increases versus test 1, the coating is very, very tight. I did keep the mesh and the nodal amount as 3 for both, but I will be varying that for my final report out. The final report outs and objectives and goals that I will be looking at is I have looked at the impact of changing the coating thickness and what that does to the Inconel 100 plate. I will also be looking at the changing the node sizes between both the zirconium dioxide as well as the Inconel 100, keeping them the same and increasing and decreasing that node size, as well as making it an uneven node size and seeing what the impact and the results of that are. The other thing that I'm going to do next and for my final project will be to go into COMSOL and 2D and 3D model the results. The final piece of this project is the validation plan and comparing the results from COMSOL models and data to the previous project, as well as verifying the results between the 1D models and the 2 and 3D models to make sure that they are close and that the comparison is where I expect it to be. That'll be part of the validation plan.